Okay, in this video, I'm going to answer some questions, solve some homework problems from section 4.5. Section 4.5 in our textbook is L'Hopital's rule. L'Hopital's rule and other indeterminate forms. So I'm just going to pick a hodgepodge of questions out of the homework, try to do a few of each type, make sure that we're all comfortable with L'Hopital's rule. Remember, L'Hopital's rule applies to indeterminate forms of the form 0 divided by 0 or plus or minus infinity divided by plus or minus infinity. And for the first few examples I'm going to work out, we will have limit problems that live in this family right off the bat. We don't have to do any adjustments, any manipulations, and then we'll practice those, and then we'll switch it up and we'll go to some of the other indeterminate forms where we might need to do some algebra prior to solving our limits. So let's just jump right in. I'll start with question number 9. I'm just picking problems randomly here. Question 9 says find the limit as t goes to 0. And we have e to the t minus 1 divided by t cubed. E to the t minus 1 divided by t cubed. This is a classic L'Hopital's rule problem in the context that when we try to plug in 0, we get e to the 0, that's 1. 1 minus 1, that's 0 on the top. 0 cubed on the bottom, we get 0 divided by 0. Now, we are in chapter 4, section 5 of our textbook. You don't make it to chapter 4, section 5 of a calculus textbook by accepting 0 divided by 0 and writing undefined for a limit problem. Those people have dropped the class a long time ago. We know that when we're doing a limit problem, it very well may be the case that the answer to this problem is undefined, but it doesn't come this easy, does it? Limit problems don't generally kick out undefined on the first step when we've plugged in whatever our limit is approaching. So typically at this point, what are we asked to do? We're asked to do some kind of algebraic manipulation. Maybe we use some trig substitutions. Worst case scenario, we use the squeeze theorem. That was our approach for limits until we learned about the derivative. And once we learned the derivative, then L'Hopital's rule comes into play. And L'Hopital's rule says if you have a limit that is of this family, 0 divided by 0 or one of the two, plus or minus infinity divided by plus or minus infinity, then if you want to evaluate that, what it says is, it says the limit of the function itself is equal to the limit of the derivative of the numerator divided by the derivative of the denominator. In other words, we can simply, I like my students to indicate that they're using L'Hopital's rule so that I know why this is, well, I'll show you what I'm talking about as I go. This is going to be the limit now as t goes to 0. We're going to take the derivative of the numerator, right? Remember, L'Hopital's rule says we take the derivative of the numerator and we take the derivative of the denominator. Do not use the quotient rule here. So I take the derivative of the numerator. The derivative of e to the t is e to the t. The derivative of 1 is 0. The derivative of t cubed is 3t squared. All right? Now I try to reevaluate my limit. I plug 0 in again. What do I get now? Now I get 1 divided by 0. Now, 1 divided by 0 is undefined. It doesn't fit one of the two formats that L'Hopital's rule addresses. Therefore, I can't apply L'Hopital's rule again. I can't keep taking the derivative. I'm only allowed to take the derivative of the numerator and the derivative of the denominator if I satisfy one of these two forms. Since we don't satisfy one of these two forms and we have 1 divided by 0, we're going to be left with the conclusion that our limit is undefined. Now, if this would again have been 0 divided by 0, L'Hopital's rule can be applied as many times as necessary. You can apply L'Hopital's rule over and over and over again as long as you keep returning back to 0 divided by 0 or infinity divided by infinity L'Hopital's rule can be used once, twice, 3, 4 times per problem. So that's problem number 9. Let's take a look at problem number 13. Problem 13 says take the limit as x approaches 0 from the right of the natural log of x divided by x. Right? The natural log of x divided by x. Now, L'Hopital's rule also applies to one-sided limits. It applies to two-sided limits. It applies to one-sided limits. As we plug in 0 from the right here, as we plug in 0 from the right, what do we get? We get the natural log of 0. That turns out to be, what? Well, if we take a look at the natural log, right, the graph of the natural log looks like this. So when we plug in 0 from the right, what do we get? We get negative infinity, don't we? When we plug 0 in the bottom, we get 0. So we get negative infinity divided by 0. All right, so that's the graph of the natural log. So we get negative infinity divided by 0. But negative infinity divided by 0 is not one of the forms that L'Hopital's rule addresses. So what are we going to have to do to come up with an answer to this problem? Well, we can't use L'Hopital's rule. We can't take the derivative of the top and the derivative of the bottom. So we're going to have to do some analysis, some good old-fashioned calculus thinking here. We're going to literally ask ourselves, what happens when we plug in a number that gets closer and closer to 0 from the right? What happens to the natural log, right? What is the behavior of the graph of the natural log? And we're going to take that and compare that to what is the behavior of the graph y equals x. Those are our two functions. That's our numerator and our denominator. Well, when we plug in 0 from the right to the natural log, we get numbers in the numerator that are negative and they're tiny, right? We get tiny negative numerator numbers. That's what we get. What happens when we plug in numbers from 0, approaching 0 from the right, into x? Well, into x, as we approach, that's the dashed function here on my graph. As we approach from the right, we also get tiny numbers, right? We get tiny numbers, but it's a different kind of tiny. This is tiny. Well, let me rewrite that. All right, let me rewrite that because I think it's going to be clear if I go with this direction. As we plug in 0 from the right into the natural log, we actually get negative numbers, right? We can all see they're negative. Instead of me calling them tiny, tiny seems to imply to a lot of us near 0. So let's just write that as negative huge. I like that notation better. I think that's going to be clearer for you to figure out on your own. What are we trying to say there? We're trying to say the numerator is growing in size. It's negative 100, negative 1,000, negative 10,000, negative 10 trillion, negative, heading for negative infinity. That's what it's doing. What's going on in the denominator? Well, in the denominator, we're getting a positive number because we're approaching x from the right. The number is going to be positive. So it's going to be positive, and here I'm going to use the word tiny. All right, I'll use the word tiny here. Now, what do I have to do to come up with an answer that's going to match the answer that's expected? I can't just say undefined. In fact, we're going to go back and we're going to readdress this problem in a second. So I don't want just undefined as a solution. I want to know where we go, right? Undefined how? Am I going to positive infinity? Am I going to negative infinity? Am I perhaps going to two different numbers from each side? What is the behavior of this function that I've asked you to analyze? Here I have a negative huge number. So I have a number that is massively large but negative, right? It's negative 1,000,000. I'm dividing that by a positive number. I'm going to get a negative number. Negative divided by positive is going to give me negative. How many times does a tiny number go into a huge number? Well, a tiny number goes into a huge number an indeterminable number of times. As this number gets smaller and smaller and smaller, this number, now again, we're not paying attention to the sign here. We've taken care of that. As this number gets bigger and bigger and bigger and bigger and bigger, and this number gets smaller and smaller and smaller and smaller, this fraction grows without bound. Imagine if the numerator was, 10 to the 10th, and the denominator was 10 to the negative 10th. Well, then when we divide that into that, we get a massively big number. We don't care about the sign. The sign is here. So this limit is going to negative infinity. Now, let's go back and take a look at this previous example because I'm feeling kind of unfulfilled with our undefined answer up there. We probably should have done an additional analysis up here and asked ourselves, what does this look like, right? We know what's happening here in the numerator. We know e to the t as we approach 0. The graph of e to the t, we can draw that graph right here, right? We know what the graph of e to the t looks like. It looks like this. This is clearly the point 1. So as we approach 0 from either side, our numerator is approaching 1. What's happening with our denominator, however, right, as we approach 0? What does the graph of 3t squared really look like? Well, the graph of 3t squared, right, the graph of 3t squared looks like this. It's a parabola that opens up, has a vertex at 0, 0. So when we ask ourselves, right, okay, I get it, it's undefined, but how? How is it undefined? Undefined in what manner? Well, we can do an analysis by looking at the graphs. If I plug in numbers closer and closer to 0, the numerator goes to 1. All right, what's going on with the denominator? Well, as I plug in numbers closer and closer to 0, this denominator, instead of writing that as 0, which indeed it is, right? Indeed it is, but it's going to a positive tiny number, isn't it? The number that 3t squared is approaching, as t gets smaller and smaller and smaller, this number, if that's 1/10, I square it, I get 1/100th. That's 3 1/100ths. That's a very small number. And of course, 1/10 is nowhere near 0. If I'm really close to 0, then 1/10 is a huge number compared to numbers that are close to 0. So we ultimately end up with 1 divided by a positive tiny number. A positive tiny number. Now, 1 is positive. A positive tiny number is positive. So when we say undefined, that's just not a fulfilling kind of answer. Undefined how, right? Undefined how? Well, we have a positive numerator and a positive denominator, so we're going to get a positive solution here. Our numerator is 1. Our denominator is a tiny number. Again, think of the smallest number you can imagine. Divide it into 1. That number goes into 1 an innumerable number of times. 1 divided by an infinitely tiny number turns out to be infinity. So a better answer to problem 9 is not going to be undefined, because that leaves the question undefined how. A better answer to number 9 is going to be the limit is positive infinity. Just like down here, we worked this one out to negative infinity. All right, so let's take a look at another homework problem. Let's take a look at let's do problem 19. Okay, what do we have here? We have the limit as x approaches 0, right? Limit as x approaches 0. We have e to the x minus 1 minus x, all divided by x squared. Right? So with every limit problem, the very first thing we always do, of course, is try to plug the number in and see what we get. If we plug in 0 here, we get 1. E to the 0 is 1. 1 minus 1 is 0. Minus 0. So in the numerator, we get 0. In the denominator, we get 0 squared, which is also 0. So this is a candidate, right? It's of the form of L'Hopital's rule. So we can work with L'Hopital's rules here. So we put an equals, we put a L'Hopital's rule down to let our teacher know that I'm going to invoke L'Hopital's rule. Now I rewrite this. This is the limit as x goes to 0. I take the derivative of e to the x, that is e to the x. I take the derivative of 1. The derivative of 1 is 0. I take the derivative of x, that's going to be minus 1, right? And on the bottom, we take the derivative and we get 2x. Now we plug in 0 again. Now what happens this time when we plug in 0? Well, we get e to the 0, which is 1. 1 minus 1. We get 0 in the numerator. Now that's not the end of the world. We got 0 in the numerator up here. Actually, I guess down here we got 0 in the denominator. So what happens when we plug 0 in here? We get 2 times 0. 2 times 0 turns out to be, well, that turns out to be 0 again. Again, we're of the form for L'Hopital's rule. So what are we going to do? We're just going to use L'Hopital's rule again. There's no limitation on the number of times you can use L'Hopital's rule. As long as it's of the form 0 divided by 0 or plus or minus infinity divided by plus or minus infinity, one of the two, plus or minus, then we can use L'Hopital's rule again. So we're going to write L'Hopital's rule to again let our teacher know I'm invoking L'Hopital's rule. So what do we get? We get the limit is x approaches 0. We take the derivative of the top, that's e to the x, isn't it? The derivative of 1 is 0, so we just get e to the x. We take the derivative of this and we get 2. Now when we plug in 0, what do we get? Well, in the numerator we get 1. E to the 0 is 1. In the denominator we take the limit as x goes to 0 of a constant, turns out to be the constant, and so the answer is 1/2. Now because L'Hopital's rule tells us the answer to the limit of f prime over g prime is going to be the answer to the limit of f divided by g if that limit begins in one of these two forms. That means our answer, right? Our answer was not 0 divided by 0 or 0 divided by 0. Those were just there to show us we were going to use L'Hopital's rule. The real answer to the problem is 1/2. So the limit is x goes to 0 of e to the x minus 1 minus x divided by x squared turns out to be 1/2. All right, so that's problem 19. All right, let's skip down, see if we can do one like, say, problem 27. All right, we'll jump in over here with problem 27. Problem 27 says take the limit as x approaches infinity of x times the sine of pi over x. Okay. Now, if we try to plug this in, what do we get? Right? What do we get? We get infinity into pi. Pi divided by infinity is 0. So that's going to be the sine of 0. That's going to be 0. However, this is infinity. This is of the form infinity times 0. Infinity times 0. Now, that is not a form that L'Hopital's rule will directly solve. L'Hopital's rule will not solve that. L'Hopital's rule says we have to have a fraction with an infinity plus or minus divided by another infinity plus or minus, or we have to have 0 divided by 0. We don't have that in this case. So what are we going to do? Well, we call this an indeterminate product. And our method for solving an indeterminate product, how do we solve an indeterminate product? Well, what we do is we say this is f and this is g, right? So we have f times g, and then we bring back some algebra 1. We say, well, the quantity f times g is equal to f divided by 1 over g. And if that's not a friendly formula, we can also write it as g divided by 1 over f. All right? So what do they want us to do, and why do they want us to do this? Well, they want us to do this because if we rewrite this as f divided by 1 over g, right, we would have, well, let's just rewrite it and see what it looks like. Let's see what that looks like. So we're going to call this f, and we're going to call this g. So this would be equal to, now we're not using L'Hopital's rule. I'm not going to write a L'Hopital's rule symbol above my equal sign. We're just using algebra here. This is going to be the limit as x approaches infinity. We're going to leave f on the top. Let's say we do that, right? And on the bottom, we're going to write 1 divided by sine of pi over x. All right? So we're using algebra and just rewriting a product as the quotient of the f and then the reciprocal of g, right? Because algebraically, that's f times g. Now, what does this get us? Well, clearly, when we plug infinity in for x, we're going to get infinity in the numerator, right? That's what we're going to get. We're going to get infinity up there. What are we doing down here? Well, down here, we're plugging infinity in for x. So on the bottom, we have 1 divided by the sine of a number approaching 0, right? Pi divided by infinity as x goes to infinity. Pi divided by infinity approaches 0, and this becomes the sine of 0. If we think about the graph, right? We think about the graph of sine. Sine, of course, goes like this, and then over here it goes like this. And as we approach 0, as x approaches 0 from either side, sine of 0 becomes smaller and smaller and smaller. Remember, we're never getting to infinity, therefore this pi divided by x is never getting to 0. So we're taking the sine of an infinitely small number. Now, what happens when we take the sine of a number very, very small, a number very close to 0? Well, when we take the sine of a number very close to 0, we get a number very close to 0. So this bottom ends up being 1 divided by a tiny number. This is the methodology or the rationale behind this approach. I have 1 divided by a tiny number. Well, 1 divided by a tiny number is, that's infinity. And because I've utilized this, I've rewritten, this expression is algebraically equivalent to this one, but this expression fits the form of L'Hopital's rule. It fits the form of L'Hopital's rule. So I can't use L'Hopital's rule here, but once I change it to this form, then I can use L'Hopital's rule to solve because we're of the form infinity divided by infinity. So we would say, all right, now I'm going to write an equal sign. I'm not going to invoke L'Hopital's rule right here. I'm going to rewrite this, right? I'm going to write this way. I'm going to leave the x there. And look at this, right? What do we have here? We have 1 over sine. 1 over sine. We could take the derivative of that. The problem with taking the derivative of 1 over sine is we're going to have to make this sine pi over x negative 1 to take the derivative of that. We don't have to work that hard. We know an equivalent expression for 1 over sine. 1 over sine is, of course, 1 over sine is cosecant. So this is cosecant pi over x. So if we bring that trig identity into play, then we'll use L'Hopital's rule, right? Then we're going to use L'Hopital's rule. And what do we get in this case? Well, let's see. We've got the limit as x goes to infinity. We take the derivative of the numerator. That's 1, right? That's a nice derivative. On the bottom, we're going to have to take the derivative of cosecant, right? And we all know what the derivative of cosecant is. The derivative of cosecant is negative cosecant cotangent. So we have negative cosecant pi over x cotangent pi over x. Right? And we're not done yet because we've got to use the chain rule, the derivative of cosecant. Okay, you're about to go through a time warp here. I'm not sure how it happened. I'm not sure why it happened, but the recording paused. So I'm hoping that I stopped recording someplace near here, paying no attention to this pink blur down here, where I can completely finish the problem and finished solving problem 27. Oh, and pay no attention to that either. So I'm just going to assume that perhaps we got to here. I'll recap. We're doing an indeterminate product example. The example was x sine pi over x, which we decided was infinity times 0, which was our indeterminate product term form. And we said, well, we should make a choice, right? We are going to take f divided by 1 over g, or g divided by 1 over f. The choice we took was to put f in the numerator and g as the reciprocal. And as you can see, it worked out to be a disaster. We had an x to start with in our numerator. Now we have an x squared. We had a cosecant in our denominator. Now, unfortunately, we have a cosecant times cotangent. The problem is growing. It's not shrinking. And so what do we do in the case of when we get a problem like this? We've made our choice, and yet instead of the problem getting better, it's getting worse. Well, what we do is we stop. Right? That's what we do. We stop, and we go back. And we rewrite the original problem, right? The original problem was the limit as x approaches infinity, and we have x sine pi over x. And what we do here is we say, all right, F, you were great in the numerator. G, you were horrific in the denominator. So I'm going to change it up. I'm going to rewrite this, right? I'm going to rewrite this as the limit as x approaches infinity. And I'm going to rewrite this as, I'm sorry, I'm paranoid. I'm looking over there to make sure the recording is actually recording. So how am I going to rewrite this? I'm going to leave the sign pi x in the numerator this time. And this time, I'm going to write 1 over x as my denominator. Now, this usually works out just fine. If f on the top, g is the reciprocal, turns out to be complicated, typically g on the top, f is the reciprocal, turns out to be nice. Let's see if that plays out for us here. So what does this equal? This is the limit as x approaches infinity. I have sine pi over x in the numerator, and my denominator is x to the negative 1, isn't it? Now, we've already completed our analysis. We started our analysis up here. We know this is going to 0, sine pi over x. We said so here. We know x is going to infinity. 1 divided by x, therefore, is going to 0. So this is equal to 0 divided by 0. L'Hopital's rule applies. So we'll come down here. We'll tell the teacher that we're invoking L'Hopital's rule. And now we will take the derivative. We'll take the derivative of the numerator. The derivative of sine is going to be cosine of pi over x. Now, we've already taken the derivative of pi over x. We did that when we were working on the blue version of the problem. What does this equal? This is equal to, if we simplify this, right? If we simplify this, this is minus pi divided by x squared. So, because we need to use the chain rule, we need the derivative of sine is cosine. The derivative of pi over x turns out to be minus pi divided by x squared. And what do we get in the denominator? Well, we have to take the derivative of x to the negative 1. Right? So what's the derivative of x to the negative 1? Well, the derivative of x to the negative 1, of course, is negative 1x to the negative 2. So if we use some algebra here, right? Let's use some algebra, see if we can clean this up. First of all, this negative up here cancels this negative down here. We have an x to the negative 2. So when I rewrite this limit, right, when I rewrite the limit, I can write that as an x squared in the numerator. Now I still have a factor of cosine, pi over x, and I still have pi times, well, look at that, x squared. Well, this x squared cancels this x squared. Remember, we can cancel any number in the numerator with a matching number in the denominator, as long as those numbers are not 0, and we're going to infinity. So x squared is certainly not going to be 0. X is going to infinity. That's nowhere near 0. Well, what do we end up with now? Well, now, when we take the limit, let's see what we get here. This is pi, so that's a constant. This, x is going to infinity, so this is pi x, pi divided by x, pardon me. So pi divided by infinity is 0, so this is pi times the cosine of 0. So our answer is simply pi. Much nicer, by the way, much nicer than what we were getting there with the blue version of the formula. Unfortunately, there's not a lot of firm rules about when do I leave this function as f and when do I leave this function as g. Which one do I put as the reciprocal? Which one do I leave in the numerator? However, if you watch the video on section 4.5, my instructional video on section 4.5, you will see there's an example there where we are given a problem and there is a definite type of function that we never put as the reciprocal. I wrote this down. This is another problem from, it's actually not from the homework in our book. It's an unassigned problem. But in my video, I do an example. We have this type of problem, an indeterminate product, and we have f times g. This is a natural log. The natural log is never used as the reciprocal function. Right? Don't use, in my experience, that just causes more and more and more complicated versions once you invoke L'Hopital's rule. So the natural log always stays in as your numerator. All right. So let me clean this off. I'll work out a couple of more problems and then close out this video. So we've looked at problems where we have L'Hopital's rule where it directly applies. The problem is constructed so that L'Hopital's rule is right there ready to be used. We've looked at other problems, right, where we had to do a division. We had to take one of our functions as a reciprocal, an indeterminate product. Let's look at a problem that, like problem 33, right? This is not going to be an indeterminate product. So what do we have in problem 33? We have a different type of problem entirely. We have the limit as x approaches 1, and we have x divided by x minus 1 minus 1 over ln of x. Okay? Now, if we take a look at this, if we take a look and just plug in 1, the numerator, we're just going to do this term right here. The numerator is going to be x. X goes to 1, so we have 1. 1 minus 1 is 0. 1 minus 1 is 0. As x approaches 1, this number right here is tiny. So we have a tiny number divided into 1. This is infinity. Minus, we have the natural log of 1. The natural log of 1 is approaching 0 as well. So we have 1 divided by a tiny number. We have here the form infinity minus infinity. Right? We call this infinity minus infinity. We call this an indeterminate difference. Right? That's not a spelled difference. All right, an indeterminate difference. Now, what is our approach for an indeterminate difference? Well, our approach for an indeterminate difference, there's two ways you can handle these problems. And it's based on what you're given as the original question. One way is you go for the common denominator. You just start right away and try to find a common denominator. This problem is a fraction minus a fraction, so it sets itself up for that approach. Another opportunity to solve these problems, or another way to solve these problems, you wouldn't use it on this problem, but another way is to multiply by the conjugate. And I'll do a problem like that as well. So let's just take this problem. So we look at this problem. We see we have infinity minus infinity. We recognize it's an indeterminate difference. We then say, okay, if I have an indeterminate difference and I have a fraction minus a fraction, I should try to get a common denominator. So I'm going to rewrite this as the limit as x approaches 1. Now my common denominator is going to be the natural log of x times x minus 1. What are we going to get on the top? Well, over here we're going to have, right, x, ln of x, minus x minus 1. Right? That's what we get when we get our common denominator. Now, if we simplify that, what are we left with? We get the limit as x approaches 1. We get x ln of x minus x plus 1, all divided by ln of x times x minus 1. Right? Now, I don't know if this has gotten any better, if it's gotten any worse. Let's take a look and see what we have, right? Let's see what we get. When we put 1 in here, we get 1. When we put 1 in here, we get 0. So we get 0 there, minus 1, plus 1. So the numerator is going to be 0. Well, how about our denominator? When we put 1 here, the natural log of 1 is 0. 0 times 1 minus 1. 1 minus 1 is also 0. 0 times 0 is 0. And voila, L'Hopital's rule. So by getting a common denominator, we were able to transform this problem into a version where L'Hopital's rule will apply. So what do? We put our equal sign down. We let our teacher know that we're invoking L'Hopital's rule. We rewrite this as the limit as x approaches 1. Now, what does L'Hopital's rule say? L'Hopital's rule says you take the derivative of the numerator and the derivative of the denominator. So we're going to do that. Remember, don't do the quotient rule. This is going to be the product rule. So we take the derivative of x, that's 1, times the natural log of x, plus x, right, x, times the derivative of the natural log, which is going to be 1 over x, minus the derivative of x, which is 1, plus the derivative of 1, which is going to be 0. What do we get on the bottom? Well, again, we have the quotient. We have the product rule. We take the derivative of the natural log, that's 1 over x, times x minus 1, plus the natural log of x times the derivative of x minus 1, which turns out to just be 1. All right, so let's see. We'll rewrite this and we'll see what we have. We have the limit as x approaches 1, right? What do we have on the top? We have the natural log of x. X times 1 over x is 1, so we have 1 minus 1 there. On the bottom, we have 1 over x times x. That's going to be 1. We have 1 over x times minus 1. That's going to be minus 1 over x, plus ln of x. Right. So what does this look like when we plug in 1? Well, when we plug in 1 here, we get 0. Here we get 1. Here we get negative 1. So our numerator is 0. If the denominator is 0, then we're just going to use L'Hopital's rule again. Let's see what we get on the denominator. We plug in 1 here, we get 1, right? Because the limit of the constant is the constant. We plug 1 in here, we get 1 over 1. 1 minus 1 is 0. The natural log of 1 is 0. So we get 0 divided by 0 again. So we'll use L'Hopital's rule again. Now we take the derivative of the numerator, right? The derivative of the natural log of x is 1 over x. This is really 0, so it's gone. What do we get down here? The derivative of this, right? The derivative of this is going to be 1. It's going to be 0. What's the derivative of this? This is x to the minus 1, right? So the derivative of that, right, if we tried to take the derivative of x to the minus 1, we would get minus 1 x to the minus 2. Now, we already have a negative, so that negative and this negative are going to cancel. So we're going to get x to the minus 2 there. And then the derivative of the natural log of x is 1 over x. Now we plug in 1 again. 1 divided by 1 gets us 1. All right, well, we're done with L'Hopital's rule because we don't have 0 divided by 0 or infinity divided by infinity. What is 1 to the negative 2? 1 to the negative 2 is 1. And then 1 divided by 1 is 1. And so the answer is 1/2. So there comes a point in time where you got to admit L'Hopital's rule is kind of fun, right? I mean, we do this because it's fun, not because anybody assigns it. We would be doing this on our own if we had nothing. I mean, you don't even have to assign these kind of problems. We just want to do them. All right, I understand how ridiculous that sounded. So let's take a look at a problem where we might want to use the conjugate, something like problem 35. Right? Here we have the limit as x approaches infinity. Right? Limit as x approaches infinity. And what do we have here? We have the square root of x squared plus x minus x. All right, so if we plug in infinity, we have infinity squared plus infinity, and then we have minus infinity. Of course, when we have infinity squared plus infinity and take the square root, we have infinity minus infinity here, don't we? That's what we have. Well, we don't know what infinity minus infinity is. It's an indeterminate derivative or an indeterminate difference, depending on which of those two lines you want to read. So what are we going to do? We're not going to get a common denominator like we did in this problem. We're going to go with the conjugate approach here. We're going to multiply the numerator and the denominator by the conjugate. The conjugate here is x squared plus x, right? The square root of x squared plus x, pardon me. And on the bottom, we're going to have the square root of x squared plus x. We're going to multiply by the conjugate. Now, this turns out, right, the numerator is the difference of two squares, and so when we multiply that out, we get x squared plus x minus x squared. Right? And what do we get on the bottom? We get the square root of x squared plus x plus x. Now, from here, what's left? Right? What's left? Well, we get the limit as x approaches infinity. Right? The limit as x approaches infinity. The numerator is just going to be x. Our denominator is going to be the square root of x squared plus x. And now when we plug in infinity into this, we get infinity on the top, we get infinity on the bottom, we get infinity divided by infinity, which is, yeah, you guessed it, L'Hopital's rule. So where do we go from here? Well, now we take the derivative of the top and the derivative of the bottom, and we see what we get. The derivative of x is going to be 1. So right now, we know we're done with L'Hopital's rule. We're not going to have another case where L'Hopital's rule is going to come into play, unless somebody from the bottom is, when we take the derivative, is going to give us a reciprocal, and we're going to be able to get an x back up on the top, because right now, our numerator is a constant. Now, what's the derivative of x squared plus x to the 1/2? Well, that's going to be 1/2 x squared plus x, right, to the minus 1/2. Oh, there it is right there, isn't it? Well, we'll see how it turns out. Times the derivative of what's inside, which is going to be 2x plus 1, right, plus 1. Wasn't this joyful? So let's see what this equals, right? We're going to do some algebra here. So we get the limit as x approaches infinity. This 1/2, we'll just put that in the numerator as a 2. Right? We'll just put that up there as a 2. What are we left with over here? We're left with 2x plus 1 divided by the square root of x squared plus x, right? Isn't that what we have there? And then, because I moved the 2 up, what I really did, of course, is I multiplied the top and the bottom by 2. Don't forget that that 2 has to get multiplied by that 1, so we get a 2 there. All right? Now, what are we left with? We've got to take the limit as x goes to infinity of this, right? Well, we know this is a constant. We know this is a constant. What's going on here? Well, we can do this problem off to the side, right? We can do this as a little aside problem. We've worked on problems like this in the past. We've done analysis where we've taken the limit as x goes to infinity of 2x plus 1 divided by the square root of x squared plus x. We know what to do. You take the highest power of x in the denominator and you divide. We rewrite this as the limit as x approaches infinity, right? Down here, we're going to have x squared over x squared plus x over x squared. And because we're going to positive infinity, we don't have to worry about taking the absolute value and getting a negative sign at the top. So we just take out the x squared. It comes out as the absolute value of x, but the absolute value of x near positive infinity is positive, so we can just write that as x. So we get 2x divided by x plus 1 over x. Now, if we simplify this, right, just do the algebra. We get the limit as x goes to infinity. What are we left with? Well, 2x divided by x is 2. Remember, we can cancel an x with an x as long as they're not 0, and as we approach infinity, they're not 0. 1 over x is still 1 over x. So we're just going to leave that here. Here we're going to have the square root. That's going to give us a 1. This, right, this is going to give us 1 over x. Now, when we evaluate that, x goes to infinity, this goes to 0, this goes to 0, and we're left with 2. So this piece right here, when we do the limit, is going to be 2. So based on that analysis there, this is going to equal 2 in the numerator divided by 2 plus 2, and that's going to be 2 over 4, which is 1/2. Hey, look at that. All the indeterminate difference problems equal to half. All right, so that takes care of an indeterminate difference example from both families. I'm going to go ahead and clean this off. I'll do one more example, an indeterminate power, and then we'll call it good for the homework solutions video for section 4.5. So what else can happen, right? What else can they ask us to do? They can give us problems that look like this. This is number 39 from the homework, right? Here's number 39. What does 39 say? 39 says take the limit as x approaches 0 from the right of x to the x squared power. Now, this is one of our indeterminate powers, we call them. Indeterminate powers. Because what is this? This is 0 to the 0. We don't know what that is. Algebra says a real number to the 0 is 1 as long as that real number is not 0. Well, in this case it is, so we don't know what that is. Other types, they don't apply to this problem, but other types are infinity to the 0, that's also not 1, and 1 to the infinity. These are our indeterminate powers. Now, I've done an example of an indeterminate power problem on my lesson for section 4.5, but this will be a second example here. So if you're looking for, when I'm done with problem 39, you're still feeling a little shaky on indeterminate powers, you can go back and take a look at the instructional video and see an example there on how to deal with indeterminate powers. So what is our approach with indeterminate powers? Well, first, we let y equal this limit. Okay? We rewrite the limit in the form of an equation. And we do that because we're going to want to take the natural log of both sides of this. Now, we can't say I'm going to take the natural log of both sides when I don't have two sides. So I'm going to rewrite this as y equals the limit as x goes to 0 from the right of x to the x squared. And now I'm going to take the natural log of both sides. So what does that look like, right? What does that look like? Well, this side just turns out to be the natural log of y. This side turns out to be the limit as x approaches 0 from the right of the natural log of x to the x squared. Right? We have a limit law back in chapter 2 that nobody remembers that talks about continuous functions and how if we have limits of continuous functions, we can take the function of the, wow, that's almost not English. But let's try that again. We have rules back in chapter 2 that says we can take and put a continuous function inside of a limit. And that's what we're doing here. So where do we go from here, right? Well, we're taking the natural log of somebody to a power. We're going to use our limit law, rewrite this, right? Rewrite this. And we can rewrite this as x squared times the natural log of x. Because we have that limit law, right? We have the limit law that says if you have the natural log of a to the r, that's equal to r times the natural log of a. Right? That's our limit law. Back limit law. That's our logarithm law. Totally lost my train of thought now. So let's see if we can get it back. So what are we going to do here, right? As this goes to 0, this is 0. 0 squared is 0. But we remember from the graph of the natural log, the graph of the natural log does this. That's going to negative infinity. This is one of our indeterminate products. This, right, this is 0 times negative infinity. And we know what to do with that. We call this function f, we call this function g, and we've already had a small we did a small conversation right here. I wrote it in green. I pointed out we never write the natural log as the reciprocal function. So we're going to rewrite this using our, right, f times g equals g divided by 1 over f algebra approach. And we're going to rewrite this as the limit as x approaches 0 from above. And what do we have here? Right? We have the natural log of x divided by 1 over x squared. Right? Always leave the natural log in the numerator. Now what does this turn out to be? Well, this is the limit. And I'm not doing anything here. I'm just going to rewrite this. This is the limit as x approaches 0 from above of the natural log of x divided by x to the minus 2. What does this give us? This gives us negative infinity and infinity. So we're going to get infinity over infinity. So this is a form of L'Hopital's rule, right? What does that get us? Well, that gets us our big equal sign with our L'Hopital's rule, and we get the limit as x approaches 0 from the right. We're going to take the derivative of each of these. The derivative of the natural log of x is 1 over x. The derivative of x to the negative 2, right, x to the negative 2, is negative 2 x to the negative 3. So what does this look like? Well, this is the limit, right, as x approaches 0 from the right. And we have 1 over x, right, 1 over x. And on the bottom, we have negative 2 over x cubed. Well, if we do our algebra, right, that's going to be the limit as x approaches 0 from the right, and we have 1 over x times x cubed over negative 2, which gets us the limit as x approaches 0 from the right, and we get x squared over negative 2. Well, we like that limit, right? You put 0 here, you square it, you get 0 divided by negative 2, you get 0. Now, be careful, all right? Be careful. This happens all the time. As a teacher, I've taught calc for 20 years. I've seen it all, and you know, some of the things I see and I just can't believe, and other things I see and then they break my heart. Well, I'm not break my heart. It's not like it's a sad puppy moment or something like that, but at least, well, it could be a sad puppy moment when you get your test back, because you get to hear, you've done all of this work, and this work is perfect. It's solid, it's organized, it's presentable. I can read this, I know what you've done. Unfortunately, if you stop here, you don't get the correct answer. And the reason you don't get the correct answer is, way back here, we said the natural log of y equals 0. You were asked to find y. But instead, you found the natural log of y. So we have to add one little caution to working out indeterminate power problems. Remember, when you take the natural log of both sides, you have to undo that process, right? Right now, we have this. We have the natural log of y equals 0. And so we don't have this. This is y. Y is equal to the limit we were asked to find. We have found the natural log of y. Now, we know what we take the log of to get 0. We know this means y equals 1, right? Y equals 1. So from there, now we can say, right? Now we know, because from over here to over here by the transitive property, right? What do we have? We have the limit as x approaches 0 from the right of x to the x squared equals 1. Now we have the real answer. So we don't want to do that to ourselves on a test, because those kinds of things on calculus exams cause us not to like our calculus teachers. And it's not our fault. We didn't do it. In fact, we pointed out to you during class not to do that. But instead, you know who gets blamed. We get blamed. It's okay. We can take it. All right, so those are my solutions to some of the problems from section 4.5, L'Hopital's rule. I hope you find this helpful.